Hi there, and thanks for tuning in. My name is Burns Foster, and I'm the product manager for Hips and SIPS. This is the first in a series of videos about the Hips and SIPS 10.0 release, and first up is variable resolution. So to set the stage for variable resolution, the original challenge that drove the development of it is all about remotely sensed data. Whether you're dealing with acoustic systems or light-based systems or similar, the data that comes back from these systems is not regularly spaced. And generally, to efficiently model any kind of remotely sensed data, we need regular spacing. So several techniques have been developed over the years to deal with this problem. One of the most common is by dividing models by depth range and their associated resolution. So we take something that's in a shallow area, say, near the surface, where we can get a very high resolution from the source data. We can do a high resolution model. And as you go deeper, you get further away from the sensor. You have to go coarser with your models. And there's some arbitrary line between those two areas that divides the two models. Of course, the problem with this approach is you're managing multiple files, multiple models around the same area, and you get discontinuity near the boundaries. So you can get this sort of feathering effect, and creating derivative products from these models becomes a challenge. TINS is another approach to modeling different data set densities. Of course, TINs are typically done in memory, which limits them in size, as in how big they can be based on your computer specifications. Holidays are also a problem. They tend to get filled in by TINs. And edge removal. Most TINs use Delaunay triangulation, and you get the long edge effect around the outer boundaries, or of course internally as holidays as well, and you have to typically manually remove those. So neither of these is a very good fit approach. So this led to the development of variable resolution. So with variable resolution, we can model an entire area from shallow to deep, or very fine to very coarse point spacing, in a single continuous model. You don't have to split your data sets up. And of course, this brings workflow efficiencies in data management, in file management, and of course, creating derivative products from those models becomes much easier with a single grid. So before we dive into defining variable resolution, we'll start at the basics with what is a surface. So a surface is effectively something that defines a value, every value within a continuous area, and those values are defined explicitly at nodes. And a gridded surface has regular spacing between those nodes defined by the resolution, and then a mesh defines the values anywhere else. So if we need to interpolate a contour, for instance, across a grid, we use some sort of linear interpolation between the points. So as an example, we lay down some grid at some appropriate spacing. We interpolate a value at every node from the source data based on our gridding method of choice. And then when creating products from that grid, we do some sort of linear interpolation or similar between those grid nodes. So that's how we create products today. Variable resolution isn't that much difference. We still define a value, every value within an area, explicitly at nodes, but variable resolution has regular spacing within a tile, with the resolution of every tile defining that spacing. And then we use a mesh to define values everywhere else and stitch it all together into a continuous model. So creating variable resolution surfaces is a multi-step process. So where do we get these tiles from? In CARIS variable resolution, we use a quad tree structure and put that into what we call a resolution map. So we take a region and some source data, and we start building a quad tree over that region. The quad tree is broken down roughly based on how many points are in each tile. So very high density areas will break down into a lot of smaller tiles, and in, say, deeper areas, you'd get several coarser or larger tiles over the same region. Then once we have those tiles laid out, for each individual tile, we compute an independent resolution by a variety of methods, basically broken down by point density or depth range. So this is what a resolution map looks like inside the application once you've generated it. You can see the blue regions are the individual quad tree tiles, and then within each tile we have a computed resolution in red. So the resolutions are completely independent between tiles. They're not fixed to any scale or any other pattern. each one is completely independent from the next. And this gives us the optimal resolution within a small region across the entire area. So there are three methods of computing a resolution map in CARIS variable resolution. The first is analogous to what happens today. You effectively break down the resolutions based on the depth of the data. So the user provides a depth range list. You can see in the upper right. So going from deep up to shoal, from the bottom of that list up to the top, we have a specific depth range and we assign it a specific resolution. When the resolution map is generated, the tiles are laid down, and then for each tile, we look at a couple of statistics. You can pick which one to use, whether it's the median or a mean or a minimum, etc. And then we use that statistic to look a value up from the table you provide. So in this example we have on the screen, it's a typical layout of a very fine resolution in shallow areas and going coarser as you go deeper. And this is roughly the end result coming out of that. So this is the most analogous to how things operate today, and we think of it sort of as a stepping stone for our users to get into variable resolution. So the next two methods aren't based on this a priori assumption about what the resolution of a given depth range should be. So the next two methods are instead purely based on point density, and you identify a target density for the grid nodes within each tile. By default, it's 20 points, so you average 20 points per node within a given tile. So with the CARIS density method, we start with a very fine binning, and that's a fraction of a millimeter effectively, and we put all the points into those bins, and we start collapsing those bins together until we reach the user-defined target density. So we collapse those points together until we get to, say, an average of 20 points per node. There's some smarts in there. Of course, we ignore empty areas, and we try to distribute the weighting. So if you have one high density spot, that tends to be ignored. So you get the optimal resolution at every point in the tile. And you end up with something like this. So this is a rec development survey from the Shallow Survey Conference 2012 in New Zealand. I'll show the VR surface from this later on in the demo, but effectively that's a shipwreck on the right. We have lots of data over the wreck itself, and then in the region around the wreck we have coarser data, fewer points. So you can see the grid node spacing is very fine on the wreck itself, and then in the lower density areas around it, the grid resolution drops off in each tile. And we have a similar density method from Calder Rice that takes a slightly different approach to estimating the resolution. Instead of starting with the superfine bin, the Calder Rice method attempts to calculate the insonified area within each tile, and then calculate the resolution to get to your target density from that. So in the lower left, you can see we have two tiles over a given set of multi-beam data. We identify roughly what the area coverage is. We just need an approximation, and from that we can establish what the resolution needs to be to get, say, 20 points per node. So both density methods actually provide very similar results. Each one has their own pros and cons, but we provide both as an option to the user. And the Calder Rice result comes out looking something like this. So the first step of creating the resolution map happens independently from the next step, which is actually doing the gridding itself. So here we use traditional gridding methods, things like a simple statistic that would be, say, shoalest depth or deepest. We also have inverse distance weighting, the swath angle method from HIPS, and of course cube. So you can cube or any of the other gridding methods with variable resolution, and it's completely independent of the estimation method used in the first step. So once we have the resolution map computed, the resolutions defined, and then the grid values calculated, we store that in our Caesar format. And that Caesar format has been something that's been around for a few years now. A very robust storage system that handles very, very large volumes of data quickly and efficiently. We use a tiered pyramid resolution storage internally, which effectively allows us, when you're at a very low resolution, or sorry, a low scale, looking at a data set, it's not paging in the entire data set, you're looking at a coarse representation, and as you zoom in onto the data set, it's paging in finer and finer data. This allows us to very quickly and efficiently display data without waiting. So we have the same benefits with variable resolution that we've had for several years with raster in the Caesar format. And the last step is when the Caesar data is stored and then read back out to display to the user, we create an on-the-fly mesh to display the data, the stored points, as a continuous surface. And the same thing happens when we're generating any products. So the mesh itself that we create across these disparate points is not stored, not persisted inside the format. It's created on the fly, on demand. And it's totally dynamic in the display. So again, with the multi-tiered resolution inside the format, at a coarse scale, you'll see a coarse representation in the mesh, and the mesh itself will refine as you zoom in. So we'll see an example of that here in a moment. And to see a bit about how that mesh works, here's a stored data set with 3 tiles, one big one across the bottom and 2 smaller ones in the upper left and right. We have our stored node values, and you can see the yellow defines the tile boundaries, and the mesh simply stitches it all together and provides us a single continuous grid. A continuous model, sorry. Another useful aspect, besides displaying the resolution map in the application, we also have the resolution at every node stored as an attribute band. So you can actually query, perform computations, and similar things on the resolution value at every node. So here's an example of a charting survey, shoal depths on the right, or sorry, on the left around an island, going deeper as we go to the right towards the black area, which is the coarser resolution. I'll pop up this data set here in a moment. In terms of workflow, this is effectively a drop-in replacement for raster surfaces. So it's up to the user whether they want to go the traditional fixed resolution raster route or they want to use variable resolution. We tried to make the workflow as seamless as possible. So you pick one or the other, or even both. You can mix and match. In terms of your processing workflow, most of the common tools in HIPS and SIPS for processing are hooked up to work directly with variable resolution in addition to raster surfaces. So the workflow is efficient and easy as possible. Okay, so let's pop up some data and have a look at what these surfaces look like in the application. This is the example from the last couple slides in the presentation. I have a charting survey with shallower data on the left, deeper data on the right. And this is what a variable resolution surface looks like. First up, let's take a peek at the resolution map I discussed in the presentation. So this is the first item that's created when creating a variable resolution surface. It's a layout of all the tiles and resolutions that we're going to use to build our surface. So this is a high-level view of the quad tree, and as I zoom in, I'm basically moving down the quad tree into smaller areas. The blue means I'm at a middle tier, and as I move in, the surface and the tiles start to break down until I reach the bottom. So when it changes from blue to opaque, that's where I'm at the lowest level of the pyramid, and I can see how CARIS VR laid out my resolution tiles. I can also turn on the grids within each tile and see the actual grid spacing inside of each tile. So that's how the quad tree breaks out. For the surface itself, by default, it's displayed as your traditional surface. I can also change that and display it as a wireframe without filling in the edges. So here's where I can really see how the modeling worked out and the disparate resolutions, the varying resolution per tile as I pan across the data set. And we can see how it's all stitched together. As I zoom in and zoom out, again, we're moving up and down the middle resolution pyramid inside the Caesar format. So here I'm paging in one of the coarser levels, and that's going to refine as I zoom in on the data set. So that's what keeps the display fast and efficient. I can also pop this up in 3D. And as I would expect, in the shallower areas, my resolution is very fine, particularly around this island where I get into some really finely spaced data. So the resolution accordingly within those tiles goes fine. And then as I go deeper, the result gets coarser. When you're creating these variable resolution surfaces, I mentioned already you can mix and match the resolution estimation method. So here we have my Calder Rice, my CARIS, or my depth range. And for the gridding, we can pick between inverse distance weighting, cube, and a few others. So the options are all there in terms of product creation, and you can use what works best for you. Another good example is the Wellington Rec. So this is the data set I had up in one of the other slides for the CARIS method, where we have a rec development survey with very high density data over the rec itself, and then going coarser in the region surrounding the data set. So if I turn on the resolution, I can see how that plays out with the varying resolution across the data set. This was the CARIS density estimation method, so I've got very dense data across the rec itself, and around the edges it starts to feather out to a coarser resolution until it drops down. So let's look at these values. We have a 0.8 meter resolution roughly around the outer edges. As I get over the rec itself, we get down to 25, 26 centimeters, 30 centimeters in spots. So it varies depending on the point density. And again, if I really want to see how this is all playing out, I can color by, I can turn on the mesh display and zoom in on some of these areas. And we can see, again, the coarse versus fine tiles and how that affects the model. So this is a good example where you've got rec development, high density data that can support a very fine resolution versus your flat regions where you don't have as much points but don't really care. And instead of making a compromise and making multiple products for the same region, you can make one single continuous product for the whole area. So thanks for tuning in. That's the end of the webinar, and we'll have more coming here in the new year.